The question says that a bar magnet of magnetic moment 1.5 joule per Tesla lies aligned with the direction of a uniform magnetic field of 0.22 Tesla. What is the amount of work required by an external torque to turn the magnet so as to align its magnetic moment normal to the field direction and opposite to the field direction? And what is the torque on magnet in case 1 and 2? So here the question is saying that we have got a magnet which is under uniform magnetic field. So if we assume this to be the uniform magnetic field and this to be the magnetic axis, now we have to find amount of work required by an external torque to turn the magnet so as to align its magnetic moment normal to the field direction. So initially it was aligned in the magnetic field. Now we have to turn this magnet so as to align it perpendicular to the magnetic field. In the first case, normal to the field direction, and in the second case we have to align it opposite, that is from this state to this state. So upon turning the magnet normal and opposite, we have to find out what is the work done by external torque that is required. And the second question, we have to find out what is the torque on the magnet in case of 1 and 2. Now in second case we have to determine if we have turned this magnet, then what would be the torque acting on this magnet. In the first case like this in 90 degree, and in the second case that is theta equals to 180 degree, where theta is the angle between the axis of the magnet and the uniform magnetic field. Now we know that torque on a magnet is given by tau equals to mb sine theta, where m is the magnetic moment, b is the magnitude of the magnetic field, and sine theta, where theta is the angle between the magnetic moment of the magnet and the magnetic field. We also know that work done by external torque is equals to final potential energy minus initial potential energy, and the magnetic potential energy is defined as U equals to minus mb cos theta, where m is the magnetic moment, b is the magnitude of magnetic field, and theta is again the angle between m and b. So let's proceed to solving. So work required by the external torque in aligning the magnet normal to the field, that is from theta equals to 0 degree to theta equals to 90 degree. We will find the initial and final potential energies. Initial potential energy will correspond to the theta equals to 0 degree, and final potential energy will correspond when theta equals to 90 degree. So using the formula above, we have calculated U initial, that is equals to minus 0.33 joule, and U final would be equal to 0 joule, because cos 90 would be equal to 0. Now work done would be equal to U final minus U initial, and that would give us 0.33 joule. Now similarly we will proceed to the second question that said that from theta equals to 0 degree to theta equals to 180 degree. So using the same approach, we will find the U initial, that is when theta equals to 0 degree it would be equal to minus 0.33 joule, and U final would be equal to 0.33 joule. So the work done would be 0.33 joule minus of 0.33 joule, that would give us 0.66 joule. Now the second part question said that what is the torque on the magnet when theta is equals to 90 degree and when theta equals to 180 degree. So we saw earlier that torque is defined as mb sine theta, or the cross product of magnetic moment and the magnetic field. Here m is the magnitude of magnetic moment and b is the magnitude of magnetic field, and sine theta, where theta is the angle between m and b. So when theta equals to 90 degree we will get torque of 0.33 Newton meter, and when theta equals to 180 degree we will get a torque of 0 Newton meter. Or visualizing this, when the magnet is in this state we will get a torque of 0.33 Newton meter, and when the magnet is in this state, that is opposite to the magnetic field, we will get a torque of 0 Newton meter. We also know that this position is the unstable equilibrium position. Thank you.